Hey guys, my name is JC and today we are going to discuss the part 2 of research interpretation. If you have not watched my last video, it's my humble request that you do so because we discussed quite a bit and it would make it more easier for you to understand what we're going to discuss here. Okay, so let's get started. In the last part, we discussed types of study. I'm just going to do a quick brush up. So we saw case studies. We saw, lab studies, which is lab analysis, chem analysis, and in vitro, in vivo, mechanistic studies. Then we saw case control studies. Then we saw cohort studies, which is observational or epidemiological studies. Then we had RCTs. And double-blinded RCTs, and then we had systematic reviews. Then we had meta-analysis and Cochrane. Okay, and we graded this based on the EPM, which is the evidence-based medicine pyramid, and we said, look, these are the weakest evidence, and as we move to the top of the pyramid, sorry, I've done it upside down, the evidence becomes the highest. Okay, so typically when somebody quotes a study, when they're making an informative video, you have to also see the kind of evidence that they are presenting. If they're basing their entire argument on the basis of, let's say, case studies or lab studies, then you can safely discard that information because they will not hold as much weightage as it would if they would be presenting you systematic reviews and meta-analysis or a bunch of RCTs. Okay, so if this is clear, then let's move on and try and understand how do we do research interpretation. But before that, we have to understand a format of a study. So a study would typically have a title. It'll give you some background as to why the study was being conducted, right? And it will talk about the methods of how the study is being conducted, if it's an RCT, if it's an observational study, the subjects and all those things. So it will give you some background into the methods. Then it will talk about data. Then we'll have a discussion and likely a conclusion. Okay, so I'm just adding abstract also. And then it will have funding disclosure, then it will have conflict of interest disclosure, and all of these things really do matter because for example, you can have like one of the best studies, but if it's published in, let's say, a shady journal with an impact factor of less than 3, and if it has large funding biases, then everything can be falsified, right? So all of these things are very important to understand. Conflict of interest, and then obviously you'll have references. So this is a typical structure of a study. And now let's get into why do we really conduct studies. If you watched my last video, I told you that we do studies primarily to gather evidence. And evidence itself can be graded. Evidence is not absolute truth. Evidence helps us get closer to truth. So evidence is basically a probability of truth. And evidence helps us in either refuting or supporting a hypothesis. Now, a hypothesis or a claim is basically what is the primary or the central thesis of any study, right? So when we conduct a study, we basically try and prove or refute a hypothesis. For example, in this case, let's assume that Shilajit boosts testosterone. Okay, so we want to conduct a study that suggests that Shilajit boosts testosterone. Okay, now our hypothesis is going to be divided into two parts. So first would be called as a null value hypothesis, or H0, which will say Shilajit does not boost testosterone. Okay, and there will be alternative hypothesis, one sec, which is represented by HA. it will say Shilajit does boost testosterone. So now this is basically the central theme of a study, right? So in the study, what we are essentially doing is we are trying to reject the null value hypothesis, or reject HO, which is called the null value hypothesis. If we are able to successfully reject this null value hypothesis, it automatically proves that our alternative hypothesis holds up, which means that Shilajit indeed does boost testosterone. Now, how much does it really boost? What's the effect size? What is the clinical significance of it all? That we will see later on. But for the time being, understand that in a study, you have to prove that your alternative hypothesis is true, and you have to reject the null value hypothesis. So if the hypothesis is Shilajit boosts testosterone, then the null value hypothesis would be that Shilajit does not boost testosterone. And throughout the study, basically what you have to do is you have to reject the null value hypothesis, and that will automatically prove that Shilajit boosts testosterone. Okay, so our primary objective in a study is reject null value hypothesis. And how do we reject null value hypothesis? By simply telling that the results are happening not primarily due to chance, but actually there is something which is there in the Shilajit that is causing these effects, right? So the world is like distributed between chance and, let's say, something order. Okay, so something can cause something, right? So causation is established when we establish that something is not happening via chance. For example, an apple falling from the tree, that would be largely a matter of chance. There's no predictability, you can't predict it. But let's say a spacecraft flying at a speed of XYZ will take XY number of hours or XY many of days, that can be predicted because there's a science behind that, right, which we can explain, right? So if we have to reject null value hypothesis, what we have to do is we have to prove that whatever is the outcome, it's not happening via chance. And to do that, we use something which we call as probability. Okay, so assume probability is written as P. So if we can successfully prove that the chance of this happening is less than 0.05% or less than 0.05 or less than 5%, which means 95% of the results are not due to chance, then we have successfully rejected the null value hypothesis. Okay, so that's what you see in the studies. If you go, you'd often see this p-value, and you'd see the p-value less than 0.05. This means there's a less than 5% chance that this is happening due to randomness, and 95% of the chance it is not due to some randomness, but there's an effect. Okay, so you'd see typically p-values which are 0.05, 0.01, and all these are good values, right? But let's say a p-value comes to be less than 0.2. Now this means that there's a 20% chance that this is happening due to randomness. Okay, so this study is kind of not good because you are not able to successfully reject the null value hypothesis. Okay, so p-value, at least 95% of the effect should be due to non-chance. Okay, so less than 0.05 is kind of considered a good standard for evaluating a study. Okay, so I hope we understood what is a null value hypothesis, then alternate hypothesis, and that we have to basically reject null value hypothesis by telling that all the results, 95% of the result is not due to chance, and maybe less than 5% is due to chance, but 95% of it is not due to chance. Okay, so we also understand p-value. Okay, now let's get deeper into some statistical concepts, and before I teach you how to interpret data, you must learn some basic statistical terms. Okay, so we'll just do a very surface level or high level overview of statistics from our past. Okay, so imagine a class where you have 5 students, and the principal comes in and asks my teacher, what's the average amount of marks that the students are getting? And let's assume that the students are getting marks somewhere like 10, 30, 20, 40, and 50. Okay, so the teacher will say, hey, my students are getting average marks of around 30. Okay, so what the teacher did is basically added these and divided them by the number of students. Okay, that becomes your average or mean. Mean is also written as mu. So average is basically sum of these values and then divide by the number of values. Okay, so this basically, in this case, 10 plus 20 plus 30, 40, 50 divided by 5, so you'll get the value as 30. Okay, so the mean or the average marks that the students are getting in the class would be 30. Now in certain cases, because sometimes the mean can be skewed because of let's say values which are deviating far from the central values, we can use something called as the median. And median, in median, what we do is you basically order the values in terms of ascending order and then you do it, right? So instead of writing 10, 30, 20, it's a 10, 20, 30, 40 and 50, and what we do is we find out the middle value. So in this case also median is 30. Median and average values usually would differ if there are larger data sets, but in this case, because both the values are the sample size is pretty small and the values are centered around the average values, so you have both the values the same, but median and mean are two things that you're going to need. Now the principal will say, hey, the average value is 30, but how many students are centered around 30, right? So the teacher will say that the students are getting average of 30 plus minus 15. So in this case, 15 becomes something what we call as standard deviation. Okay, so standard deviation has a formula which I'm going to write it here. SD is basically square of x minus mu square and minus 1. Now again, x is going to be individual values, so data and data point, and then you have mu, which is the mean, and n is the total number of data points. So total number of data points. Okay, now a good distribution of data would look something like this. Okay, so this is referred to as the bell curve. So imagine if this mean was 30, then you would have values on either side of the bell curve, and you would see values like 40 here, you would see 20 here, you'd see 10 here, and you would see 50 here, right? So this is a good bell curve distribution, and this would be desirable in any kind of data. But let's say the data is not distributed in the shape of a bell curve but has a more flattish curve. Okay, let's assume that this is the values which are coming, right? So you have like 30, you have like 25, 21, something like this. Then this kind of becomes difficult to measure, because what we want to do is we want to have more and more data which is kind of converging towards the mean value. Okay, so in this case, this kind of graph would not be great, and I'll also mention some other kinds of graphs here. The point I'm trying to make is that the data needs to have a normalized distribution. A bell curve should form, which means that most of the values that you see in the result should be centralized around the mean. And if the standard deviation is too high, let's assume, to give you an example, let's assume the research is that Shilajit consumption results in a boost of testosterone levels by 100 ng per dl plus minus 10. It means that most of the values are centered around the mean distribution. So if we have to draw a graph, it would look something like let's say this. Okay, because most of the values, and I'm assuming that this is let's say this is 100 ng per dl, most of the values would be centered around this bell curve, right? Because 10 is pretty small, right? So you'd have values like, let's say 110, and you'd have 90. Most of the values would fall between this range, and obviously you'll have some extreme values, but see, this will not skew the mean score substantially. But let's say there was a scenario where the standard deviation was too high. Okay, instead of a standard deviation of plus minus 10, let's say somebody says the values were plus minus 100 ng per dl. Now this is problematic because what is happening is that in this case some people are getting their testosterone levels boosted up to 200 ng per dl, while some people are also reducing their testosterone levels by 100 ng per dl, which means on a net basis this result cannot be trusted. There's the values are not centered around the mean. They are very widely distributed, right? So you'd almost have and again, because this is minus ng per dl, right? So you'd see that the bell curve will shift and you'll have like this wide kind of a range where it would be very difficult for somebody to trust the data. Okay, so let's see this going all the way on the negative side of the spectrum. Now this kind of a tendency, this is not good data. Okay, so what you want is you want your standard deviation to be small as possible, and most of the values should be centered around mean, right? So a good data would have a really good central tendency and it will be reflected in the bell curve. Now I know these concepts can get a little bit tricky, but as you keep practicing you'll get a hang of these. So next we have to discuss and variance, obviously. So variance basically is a measure of how much is the variance in the results. Okay, so it's just a square of SD, which is standard deviation. So if your standard deviation was 15, your variance would be somewhere around 250. Okay, so variance is basically square of standard deviation. Okay, so now we have understood basic stats, we have understood hypothesis, and we have understood p-values. Now let's also look at some of the tools that are used, and we'll obviously discuss correlation, causation in a while, but before that let's also discuss something called as I-square. Now this is something that's very important and it's a measure of heterogeneity. Okay, when you look at systematic reviews, what they do is they typically take up multiple studies, multiple RCTs, and they plot the results. And sometimes the results would be something like this. They'll have, this is a tree plot, and you'd see some studies showing results better, some results. So some of the studies will see positive results, some studies will show negative results, right? So basically there's a measure to check how consistent the studies are. So we measure that using I-square. I-square is a measure of heterogeneity, right? So I-square less than 50 would means that the studies are providing consistent results. So less than 50% is roughly consistent. And if I-square is, let's say, greater than 70-75%, this means there's considerable heterogeneity. And you can't say that these results are consistent, right? So this is something I really bank on, especially when it comes to systematic reviews and large meta-analysis, for example, the collagen study. And we are going to use all of the concepts that we are learning in this and the last video, and we'll apply it in the third session where we'll actually deep dive into real studies, right? So this is something I bank on whenever I'm referring to systematic reviews. And there's multiple other such factors. You have tau, you have chi-square, so different kinds of measures. But I-square is one of the most basic. So I-square is heterogeneity, right? So whenever you are assessing systematic reviews and meta-analysis, I-square is one thing you should look at. It provides you insight into how consistent the studies are. Now, the consistency of the studies can vary on different kinds of things. So then there's further, subgroup analysis and all those things, which we don't really get into. But for the time being, remember, I-square is heterogeneity. Right. Apart from this, let's also discuss effect size. So remember when we were talking about Shilajit increases testosterone. Sure, let's assume that we have results where P is less than 0.05. Okay, so we have already rejected the null value hypothesis, and we somehow come to the conclusion that Shilajit does boost testosterone. When we look into the data, we realize that, okay, Shilajit boosts testosterone levels by 3%. Okay, now 3% is peanuts. 3% is peanuts because this is going to be clinically non-significant. Okay, because there could be many confounding variables. It could be like, just regular basis, 3% increase in testosterone levels is not really much. But if the study were to prove that, Shilajit increases testosterone levels by, let's say, 20%, that would be considered clinically significant. Okay, so this is a measure of basically effect size. So how do we measure effect size? We measure effect size in terms of, there are different ways, but typically in this case, measure it in the form of percentage. So for example, let's assume somebody's mean testosterone levels were 300 ng per dl, and there was a difference. So post analysis, the study measured a difference of let's say 320 plus minus 10 ng per dl. Okay, so 300 to 320 ng per dl, roughly 3 to 4% increase, which is not clinically significant. So the effect size is basically 3 to 4%, okay, or 0.3 to 0.4. Now another thing that we have to learn about is confidence interval. So confidence interval basically tells you the likeliness of ranges. So for example, in this case, most of the results will fall in a range, or the effect size is in the range. So confidence interval is typically referred to as 95%, and then the results are, let's say, you can mention your absolute range or you can mention the effect size. So I would say, let's say 0.2 and let's say 0.8. Okay, so there's a 95% confidence that the values fall between 0.2 to 0.8. Okay, now confidence interval typically should be non-zero. When it gets less than 0, then we have the confidence is not there. Okay, so this is again a measure of evaluating the sanctity of the data. Okay, so we've learned what? We've checked the I-square, which is heterogeneity, we've checked the effect size, and we've checked the confidence interval. So now what else can we look into it? So again, once you have access to the data, you can evaluate all of these things. You can understand if the data has a central tendency. You can check the results effect size. You can see if the results are clinically significant or non-significant. You can also check them for their confidence interval. If you're looking for meta-analysis, you're looking for, let's say, systematic review or even subgroup analysis, you can check out the heterogeneity. And yeah, and we've learned basic stats. What I want to do is I want to cover a little bit about funding biases. So funding biases, what we do is we look at funnel plots. Actually, risk of biases. So ROB, risk of bias. So all studies can have different kinds of funding biases. They can have different kinds of conflict of interest. So typically referred to as risk of bias. And then we have funnel plots. In this, basically what we do is we look at the studies, and the studies have to fall in this category. So you gotta cover both the negative studies as well as the positive studies. And when the studies, let's say, are like this, okay, so you have negative studies, you have positive studies, so it kind of forms a funnel plot. Okay, so whenever you are evaluating a systematic review, you have to check for funnel plots, and this will help you understand if the systematic review is considering all studies, good and bad, and it's not doing cherry picking. Okay, if it is doing cherry picking, in this case, your funnel plot will have more values on the positive side and less values on the negative side. Okay, so in this case, the funnel plot would look something more unbalanced, and the risk of bias will go up. Okay, so this is something there. Then conflict of interest is something that you have to look into the background of the authors. Conflict of interest, you have to evaluate who are the authors. Did they hold any kind of position, or they're associated with the organization in some capacity, right? So there's these kind of things also which we have to evaluate. Now, I hope this gives you some brief insight into how complicated it can get sometimes when you really have to look at the data in detail. And yeah, so because you know what happens is most of the times when you are watching these reels and videos, most of the people will just look at a study abstract and they'll give you the conclusion from the abstract, when in reality there's much more which is going on in a study. Now in the next video, what I'm going to do is I'm going to talk about some major fallacies. We'll probably discuss fallacies and arguments, or maybe what we can do is we can take it up next, or maybe next to next, I don't know, because this is going to be a chapter in itself. So fallacies, common logical fallacies, and then what we're going to do is what we have learned so far, apply that in actual studies. Okay, so that we'll leave it part 3 or part 4 of the video. We'll see depending on how long the videos get, but I hope that this little exercise has helped you understand more into what goes into researchers, how do you analyze a study, how can you evaluate them, and a little bit of how to check the data. With this, I think it's time to say goodbye. Thank you and have a great day.